Right now, a fleet of NASA spacecraft are turning their attention to an unusual object speeding through our solar system. Something astonishing has unfolded as 3I, Atlas hugged the Sun's influence in a way that seemed at first glance impossible. This interstellar wanderer, sliding into our solar system on a hyperbolic trajectory, has just executed a cosmic act that challenges every expectation about comets and how they respond to solar heating. 3I, Atlas, the third confirmed interstellar object ever observed, is full of surprises. Even from early, blurry shots, its unusual chemical signatures were clear. It's producing significantly more nickel than iron, and scientists don't know why. Detected by the Atlas survey system, its path is not a gentle ellipse but a hyperbola. This is not a body captured into orbit, but one that flings itself through, never to return. As it approaches perihelion, it draws ever closer to the Sun, and that moment promises to be the stage for something extraordinary. The recent behavior of 3I, Atlas is extraordinary because it appears to have activated in a way no other comet has before. As solar radiation intensifies, comets typically sublimate. Ice is turned directly into gas, forming a coma and a tail. But 3I, Atlas has revealed a coma overwhelmingly dominated by carbon dioxide, text, CO_2, gas. Infrared spectroscopy from JWST captured this dramatic dominance. The mixing ratio of text, CO_2 to water, text, H_2, text, O, in the coma is an extreme outlier, far greater than what typical solar system comets display. This suggests the nucleus is intrinsically rich in text, CO_2 or structured in a way that suppresses water emission. Even stranger, the comet began releasing water vapor and showing signs of activity when it was still far from the Sun, nearly 3.5 astronomical units. At these distances, water-ice sublimation is typically negligible. Strong ultraviolet emission of hydroxyl radicals, text, O, has been observed, the smoking gun, for water breaking apart in UV radiation. This requires an unusually large active surface fraction, suggesting the comet's surface or near-surface layers are unusually permeable or fractured, perhaps preconditioned by prolonged cosmic exposure. Just's observations confirm the measured text, CO_2 to text, H_2, text, O, mixing ratio is about 8, among the highest ever recorded. This suggests the comet may have formed near a text, CO_2 ice line in its origin star system. The suppressed water signature may be due to a thick insulating dust mantle or refractory crust that blocks heat conduction, preventing deep heating and water sublimation, while the more volatile text, CO_2 nearer the surface can still escape. As it draws nearer to the Sun, the comet doesn't simply emit in a symmetric halo. There is evidence of enhanced outgassing in the sunward direction, a plume preferentially pushed toward the sunlight side. This is an anisotropic sublimation front, an asymmetric release of material stronger in the sunlit hemisphere. Normally, sunlight pressure pushes material away from the Sun. This phenomenon betrays unique thermophysical properties. Even more confounding is the formation of an anti-tail, an apparent tail that seems to stretch toward the Sun. This may stem from the sunward sublimation and survival of ice grains oriented in that direction, forming a real structural feature pointing inward. Perhaps most dramatic was the signal that 3I, Atlas switched on suddenly during its approach. Some of its volatile releases are rising in a superlinear fashion, not a smooth gradual curve, but in a threshold-driven burst as certain temperature thresholds are crossed. Emissions of cyanide, text, CN, and atomic nickel vapor surge violently in a manner not simply tied to solar flux. This switch-like behavior is what gives the impression that 3I, Atlas has done the impossible. It has broken from the norms of sublimation physics. This suggests latent volatile reserves frozen at deeper layers, activating only when heating crosses a critical boundary. Polarimetric observations add another layer of mystery, showing 3I Atlas exhibits an extremely deep negative polarization at small phase angles, values and behavior not matched in typical comets. This suggests the dust and ice grains in its coma have unique size distributions, porosities, or internal structures, dust shaped by unknown, distant histories. Spectroscopic modeling suggests the coma is a mixture of refractory material akin to meteorite analogues and sizable grains of water ice. The presence of these large icy grains means the comet may carry an extended source of water, allowing the gradual sublimation of these fragments to sustain water vapor release even when the nucleus itself receives modest heat. The nucleus itself remains unresolved, but trajectory and orbital dynamics underscore how extraordinary this visitor is. Its orbital eccentricity, well above 1, cements its origin beyond the Sun's gravitational domain. Intriguingly, it travels on a retrograde path nearly aligned with the Solar System's ecliptic plane, which is unexpected for an interstellar object, hinting at a possible bias in detection or a deeper structure in interstellar debris distribution. This comet will reach its closest distance to the Sun, perihelion, around October 29, 2025, at about 1.36 astronomical units. This is the moment of maximum stress, where the Sun's heat and radiation will act most strongly, and its internal dynamics face the greatest stress. The impossible here is that 3I Atlas is crossing boundaries between comet behavior categories, surpassing expectations from solar system analogues. Its behavior could be dictated by exotic ice mixtures, unusual porosity, internal layering of unexpected chemicals, or structural brittleness under thermal stress. The fact that text $CO_2 dominates and water is suppressed relative to expectations suggests that the nucleus's thermal properties may be extreme, causing sudden outbursts when thresholds are crossed rather than smooth gradients. Because it is interstellar, the stakes are higher. This behavior, if it reflects materials or processes alien to our familiar comets, hints at how bodies in other stellar systems evolve. The rich text CO_2 content, the suppressed water, the intense threshold emissions, the asymmetric plume, the sunward features, and the exotic polarization all converge into a signature unlike anything catalogued. This suggests that interstellar bodies may be fundamentally different in composition and structure. Witnessing this event is a rare, real-time experiment. As 3I Atlas crosses perihelion, instruments on Earth and in orbit will capture its evolving emissions and spectral signatures. The interplay between solar radiation, sublimation, and internal dynamics will play out dynamically. The moment 3I Atlas did the impossible is a turning point. It transformed from a passive visitor into an active, unpredictable participant in solar dynamics. It became a real-time laboratory for studying how exotic bodies respond to solar heating, how volatile layering behaves under stress, and how material properties established in far-off star systems manifest under a star's embrace. The cosmic implication is profound. There is more diversity in cometary behavior than previously assumed. We now have witnessed an interstellar object that acts like no comet we've studied before. The unexpected interplay of text CO_2 water, asymmetric jets, and kinetics reveals that 3I Atlas is not a comet by the book. It is a messenger of alternate rules. It teaches that cosmic travelers carry legacies of their birth environments, radiation, chemistry, temperature regimes, all preserved in ice and dust and waiting to reveal themselves under stellar glare. The Sun's fierce radiance has begun to pry open secrets within 3I Atlas. And what it has revealed is nothing short of transformative for how we think about objects from beyond our cosmic neighborhood. The comet is unfolding into a being of active chemistry, shifting morphology, and volatile alchemy, behaviors that demand we rethink the boundary between familiar and unknown in comet science. The phenomenon of turning on with threshold behavior is thus not a quirk, but may be a window into how interstellar bodies accumulate volatiles, preserve them in metastable form, and release them under stress. It suggests that many interstellar comets might lurk dark, undetectable until they cross a thermal threshold where sudden, sweeping volatile release lights them up. The impact of this impossible behavior extends to planning future missions, forcing us to anticipate volatile surges, unpredictable jetting, and structural instability. The models for trajectory planning must account for more exotic and abrupt activity. As it closes in, the interplay between solar heating, gas release, dust dynamics, and nucleus structure will accelerate. We may see the emergence of jets, fragmentation events, sudden brightness surges, and complex tail morphology. By the time it reaches perihelion 3I, Atlas will have undergone the most intense heating and stress of its journey through our inner solar system. Its behavior just before and after perihelion may include peak volatile release, maximum dust ejection, and structural changes. This moment of doing the impossible is not just the comet's act, but ours. A moment forcing human science to stretch, adapt, and rethink. In the coming days, as solar heating intensifies, 3I, Atlas will continue to defy and instruct, becoming a Rosetta Stone, not for Earth's comets, but for comets born in alien disks, showing us that what we call normal is only one chapter in a vaster cosmic diversity. What do you expect next from this impossible interstellar visitor?